Hey everybody, this is Larry. This is day 12 of the August Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Group anagram. So, okay. I usually solve it live, so let me know if if you need to go fast forward, then, do whatever you need to do. Okay. So the first thing I would say is that when you see anagrams and grouping them together, what is anagrams, right? Anagram means that, well, they tell you actually. They tell you that an anagram is that a word that when you rearrange them, you basically have all the original letters exactly once. And another way to phrase that, given this definition, which is a general definition, is that there's a one-to-one mapping between two words, right, of all the characters. And when you rephrase that, it just means that they contain all the characters, all the exact count of all the characters in some order. Meaning that, in English, for example, everything here has one E, one T, one A, but it also, works if you have something like, I don't know, if that's two A's, then everything here has to have two A's, right? So that's basically the idea. And then having that set, so how would you group them together, right? There's only actually 100 N. So maybe you can do N squared. Oh, no, wait, I misread this. Okay. So there's actually 10 to the fourth N, and each of them has 100 characters. So that's going to be too slow if you try to do some N squared times M type thing, where M is the length of each string, right? But that's how you would do it naively, where you just look, okay, for every two things, see if you can maybe do a collection or a counter or something like that of a frequency map, and then compare the frequency map. Okay. So that's one way to do it. But of course, that's going to be too slow. So then the standard thing is that, okay, of grouping things together is that you're trying to find a normalization. And what I mean by a normalization is just a consistent way of for everything that, basically a function that lets you, for every input that gives you put, it allows you to get this the same key, if you will, almost like a hashing function, but in this case, there's no false positives, no false negatives. It's just one-to-one mapping. That's correct, because there's no hashing, right? But that kind of lookup is the idea behind that. And in this case, there are a couple of ways you can do this. Actually, you can actually just group them by, say, what we said earlier, the frequency map of, like, okay, for example, we look at this, we go, okay, there's one A, one E, one T, and then that's good. Here we're just one A, one E, one T, so we put them together in the same bucket, right? So that's basically the idea here. What we can do, and there are a couple of ways you can do this, but I'm going to do it the lazy way, is just sorting the characters in an array, because that's another way of having the frequency table without it. That is going to be slightly slower than putting it in a hash table per se, or a counter table, but as you see, and we'll talk about the complexity a little bit later after we write the code, that it probably mostly doesn't really matter. Okay. Maybe it does actually, but it wouldn't be that much slower. Yeah, should be okay. Yikes. But yeah. Let's get started, and we'll do the math at some point. And of course, so that means that there are places for optimizations. We'll point them out later. Yeah, I think for now, so then this becomes straightforward-ish. So we have a list of answers. Let's just say we have buckets, right? Default take of a list, but basically we're just grouped maybe. Basically what we want to do is just we create a dictionary of lists, because, and you'll see in a second, so for word in strings, so we want something that group of this normalized word, normalized, I just say normalized, is we add this to the list in which this is the normalized word. And of course we said, and we can play around with different normalization functions as we said, but that's going to be the answer. And then at the very end, we can just do group.values for the solution, right? So here for the normalization, I believe that's the case. Yeah. And for the normalization, as we said, we can actually just do sort of word. Maybe we have to join it though. Back to a word, just to be a little bit easier. And some test cases that they give you, I think I got them right. Yep, okay. I get this one right, I didn't even look at it. Okay, so, I mean, I think this is right. It's just not in the right order, or in the same order they have it, but you can return the answer in any order. And this is any order. But basically 10 is matched up with nat and bad, and these things matched up, so it should be okay. So let's give it a quick submit. Let's see how that goes. Yeah, so that looks good. But, so what is the complexity here, right? Well, let's take a look. So normalized, this depends on the length of the word, and let's say that m is the length of the word, then sorting this would be m log m. Of course, yeah, m log n, right? Oh, sorry, m log m. And here, there are n words. So what is this, right? So this is a hash function that you say is O of 1 for the purpose of keeping it simple, and then you add it to a list, so this is O of 1. So that means that, well, this is O of 1, except for that there's an m log m function here. So that means that this is going to be O of n times m log m time. And in terms of space, this is just going to be, I guess O of n times m, but space, but this is going to be linear space, because for each character in the sum of all the words, you know, it shows up once here, right? For every word, it shows up once in the thing, so it is going to be linear space. So can we optimize this a little bit more? As we said, this is m log m. It's going to be fast enough because m log m, well, m is 100, so m log m is like 1,000, right? Given, yeah. Right, so 1,000 times 10 to the 4th, it's going to be fast enough, generally speaking. But you can actually do better. You can actually do this, like we said, we can make this in the O of 26, which is O of 1, or maybe O of alpha, depending on how you want to define it, where alpha is equal to the size of the alphabet, right? And in that case, that is what we just said earlier, which is that you can maybe do something like collections dot counter of word, and then and how do you, yeah, maybe I don't think this is hashable, but if you're, yeah, this is not hashable, but I actually don't, I don't know how to do it in one liner, but you can imagine doing this to convert this counter into either a string or something like that, and then you know, you can do it with a for loop with 26, for example. You can do something like lookup is or counters, and then something like for x is in range of A to Z. I don't think this is right syntax. I'll give you, because it's not numbers, but you get the idea here of like, okay, right? Like normalized word is equal to normalized word is equal to x plus or counter of x plus x, and then return normalized word or something like that, right? I think that this part is the one that would give me an issue, but in theory that should be right. I mean, you can actually, what you should do is, yeah, what you should do is kind of convert this to an ordinal while you to make it correct. But this is, now I'm actually mostly already doing the full implementation, so fine. Let's actually finish that up. And I mean that now we have to convert this to char, and that's fine. All right. Of course, this has, as you can see, the way that we write it anyway. Oh, this is, let's convert this to a string. Just a lot of conversion. So you can probably, if you take a guess, that this has a lot of constant value things. So it's not clear to me which is faster, even though it gives the wrong right. It gives the right answer, but it's not super clear that this is faster, even though hidden behind the O of 1, the big O notation, you do hide that complexity a little bit, whereas sorting is hyper optimized in a lot of languages. So it may even be true that m log m is faster than this O of alpha or O of 1, right? Is it really? I don't know. But we're doing way more expensive stuff here, and if you have a eagle eye, you may notice that this is a little bit awkward, but you can also just like convert it into an array and then concatenate or something like that. So there are a lot of things you can do with this, but the idea is still the same, which is that we don't change this part. But yeah, so as long as you kind of have, I think the hard part is this part, and then you just have to kind of, and if you have done these kind of problems of anagrams, then it will come to you. So definitely practice that, but it's not super handy if you ask me. But yeah, if you use the more optimized way, if you will, then you have O times alpha time, and of course the space doesn't change because this is still linear space, and that is the lower bound because that's what we return, right? That's all I have for this one. Yeah, I think that's all I have for this one. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think. Show me some love. I'm almost at 500 days of Leetcode. So yeah, that must be something, right? Anyway, stay good, stay healthy, to good mental health. I'll see you later. Bye bye.